Okay, let me get started. Have two things. I had some special thing I did on concrete, but the people who were interested in the concrete aren't here yet. So I think I'll start with where I was yesterday. And this is application methodologies, and we were talking about originally the application idea for nonlinear fraction mechanics was simply to do the test in a small specimen that was nonlinear and then apply it to larger structures that may be linear elastic. Again, the applying to structures that are big and linear elastic has advantages in that linear elastic you can use superposition of stresses, and you can do a simple K analysis, which is a lot easier than doing other analysis. So let me talk about this. There are a lot of application methodologies, all sorts of things. I'll just give you a sampling of some of the things people are doing, and may seem complicated to you, and if it does, you're right, it is. Some of these things are complicated. Some of them you need software to really be able to do these things. So the two basic approaches to applications in nonlinear behavior are crack drive based and failure analysis based. And here's a schematic. In the crack drive base, you pick a parameter like load, and then you calculate the J or the K or whatever fracture parameter you're dealing with, and you make a curve then of that parameter versus the load. And if you have a critical value of K or a critical value of J, you could pick off a critical value of load. Now, in order to do failure analysis types, you have to put this upside down. And the idea of putting things upside down started with, I think, the British. You know the British. I think one of the reasons they put up things upside down is because they like to eat with their fork upside down instead of right side up. So because they spent all those years eating with an upside down fork, they thought upside down fracture approach was probably the thing to do. Here you have K ratios and J ratios, and they are the ratio of an applied value to a fracture value. And then they can develop this, and inside is safe and outside is failure. So let me show you some of the possibilities for this. There is a handbook for J. So like K, you can calculate the J. Now the number of cases involved are fairly limited. Things like single edge intention, center crack intention, and some pipe and pressure vessel geometries are in there, and they pick 4 parameters, which are load, crack length, displacement J. So you know load is P, crack length A. We've been using V for displacement J. So these two then could be a function of A and load. So given a crack length, you can develop this kind of crack drive curve. The way then is to calculate the load at J1C is one of the things you can do. And there's another way that people use J versus T, but I think I won't talk about that. I want to talk about J. So here is J versus load. Now the load is normalized, I don't say that on there, with a kind of a limit load. And it's not necessarily limit load, just a calibration load. And the load to the calibration load then is on the horizontal axis and the J on the vertical axis. Now there's a formula for picking this calibration load, P sub 0. So if you know then something like J1C, you can predict the load. Because you can predict displacement as well from this, load and displacement and J and crack length all go together, you can predict load versus displacement as well. These loads then would be for a given crack size. You would pick the crack size to start with. So we did this problem yesterday. We calculated J1C from the test data and got 1,400 inch-pounds per inches squared. So if you use the handbook, what would the critical load be? And we have a P0 of 300. So use the graph, but the graph was in kilojoules per meter squared. So I had to do all the conversions of units. The conversion from inch-pounds per inches squared to kilojoules per meter squared is 0.175. Not a very nice round number, but that's the conversion. So this is the critical value of J that we were looking for. And then the P0 over P at 245 is 105. So here's the J, here's the P over P0, 105. So since P0 was 300, 105 times 300 is 315. I don't know that this method is used very often, but it is a crack drive method and example of what you can do with crack drive. Didn't want to talk about this one. Here's a CTOD design curve, and I showed you this yesterday when we talked about CTOD, this design curve. I'll give you a little bit more detail about that. That's used a lot in England, and people at the Welding Institute started this and developed the design curve. Now when you ask them how did they develop it, where did they get the numbers from, they said, oh, it's a secret kind of thing, or from their experience. I don't know. They didn't want to tell you exactly where it came from. Anyway, the CTO design curve is based on strain. Epsilon here is the strain. And to get the strain, they use 3 values of stress. So the value of stress they use is primary membrane stress. That would be like a tension, P over area, load over area stress. Primary bending stress, that would be the bending moment, MC over I we call it. Bending moment over that is the primary bending stress. Then if you have a notch or a hole, all of those are modified by the stress concentration factor. Use a little k here. Stress concentration factor is the stress around a hole or a notch compared to the average stress in the body. So these primary membrane stress, primary bend stress are modified by that value. And then the other thing is a secondary stress. They call it Q. Secondary stress could be residual stresses or thermal stresses. Sometimes they're hard to come by. You don't know what residual stresses are unless you destroy the piece. There's methods of calculating residual stresses, but you have to destroy the piece usually. So sometimes they guess at it. And residual and thermal are the 2 main ones here, I think. Anyway, all those stresses are added together. Membrane bending times the stress concentration, and then the secondary stress, and then divide that by an elastic modulus, and you get then a strain ratio. So strain over strain thing is strain over yield strength divided by modulus. So the epsilon naught is the strain at yielding. So here is the abscissa, strain over yield strain. Here is the ordinate, the vertical, and it is a phi, which is a non-dimensionalized CTOD. Again, it's hard to read, but this is CTOD, 2 pi, yield strain, and then crack size. And normally with this formula, and the stress concentration and everything, you get strains that are higher than yield strain. So this would be strain equals yield strain, but you're off and out here. Now all this sort of clutter that they put on here are for special conditions that they worry about. But if you want to do an actual problem, you can ignore the clutter and just look at that dark line. So failure analysis curves, talk a little bit about them. They talked about the Dugdale strip yield model, and that's going to come up again a little later, but he had a case solution that's given like this. Again, this is yield stress, the log of the secant. The secant is 1 over cosine. So when the stress gets to the yield strength, you have the secant of pi over 2, which is 0. Secant of 0 is infinite. It blows up because cosine goes to 0 there. So 1 over cosine blows up, and then the log has a what we call a singularity, goes to infinity. But below that, you get a modified K, which is a little bit higher than K elastic. Now he uses this for a failure analysis diagram, which they called R6. R6 name came from the report that was first written for each year, I guess. They wrote their reports R1, R2, R3, and this was number 6 report that was written that year, so R6 was the name of the report. So they called the failure analysis diagram in that report the R6 failure analysis diagram. There are two ratios, K ratio and stress ratio, or strength ratio. Stress ratio is actual stress divided by the yield strength. K ratio is the K for a center crack panel divided by the Dugdale K. And show you a picture of it. Here's how the Dugdale line looks. If you were doing one parameter at a time, you might do like this. The K ratio of 1 means then that K is equal to K1C. So if you take K equals K1C as the failure, that's okay. Or the stress ratio of 1 means you take the stress equal to the yield strength. So that stress ratio 1 means you have failure by yield. This stress ratio, K ratio of 1 means you have failure by fracture toughness. However, if you look either or, you would get a box, a rectangular box. However, in the R6 approach, they rounded that off, and in this region then, the strength to the yield strength and the K to the K1C is put together in a way that you can't quite get the yield strength for failure or K for failure, but the combination of the two causes failure. Now anything inside here is safe. Anything outside of this dark line is not safe. Here's an example of how it looks. Now the idea of what makes it safe, if 1 over K1C, K applied over K1C, is less than 1 over K Dugdale, then K Dugdale is less than K1C. I don't know if that makes sense, but what happens then is inside here you have K Dugdale less than K1C. And outside there you have K Dugdale greater than K1C. So the K Dugdale is this equation. And it's like a regular K, only it's modified for yielding. So here would be an example. When you divide the K for center crack by K Dugdale, you come up with this equation. So in order to apply this and do a K ratio, you have to use that equation. I'm going to use that a little bit later when I play with some examples. Now the idea of failure analysis diagram this is based on K. Dugdale, was taken one step further, and the one step further was this. Some of the J handbook formulas were used to do failure analysis diagrams. So these J ratios are based on the J handbook formulas and not on the Dugdale. Here is an example for a center crack, and the handbook is based on hardening material. So this little n is the hardening exponent. The hardening exponent is put on stress, so the low exponent is high hardening and the high exponent is low hardening. So if you get perfect plastic material, you would get that n going to infinity, but 20 is pretty flat. If you would get perfectly linear elastic material, this exponent would be 1. So somewhere between 1 and infinity, you get some hardening. So this is the diagram for different hardening exponents. Didn't mention that, well, I won't go back. The handbook for J's, you have to know the material properties and you have to know the hardening exponent to do that, or you have to pick one. 10 is about an average hardening exponent, so for a lot of materials 10 is a good estimate. It's in the middle. The Dugdale model strip yield, or R6, is right here, this dashed line. So you can see if you use the J handbook, you get a little bit of leniency in that you can go past the yield. You can go, this would be material yields. You can go up to 40% greater than yield, and there are some safe regions for being greater than yield. Here's the same thing, but picking a hardening exponent of 10 and then different A over W. So in their model, 2W is the width and 2A is the crack size. You've got to be a little careful. Some people use 1W for width and some people 2W. So it depends on who's doing it. But 3A over W ratios, and again you have these curves. Here's the strip yield Dugdale model. So if you do the analysis, you really need the J handbook solutions. Anything inside here is safe, anything outside is not safe. Might point out that one of the things people liked about these kind of diagrams is they want to know how safe. If you get then say a point inside and you say, well, we're safe. Now what's the safety factor on that? You can pick a safety factor by drawing a line from here through the point, hitting the curve, and then the stress ratio at the curve divided by the stress ratio at the point is a type of safety factor. So you can in fact get a safety factor of that. If you're right on the curve itself, safety factor would be 1. Here's an example for R6. Say you have an applied stress of 60, yield strength of 100, K1C of 120, then is that safe or not? So the stress ratio is 0.6. Use the center crack model, 2A equals 1 inch in this case, and get a K. K was 75, so the K ratio is 75 over 120, K1C, 0.626, and whoops, my 0.1 is here. So stress ratio 0.6, K ratio 0.626, so 0.6, 0.626 puts it well inside the curve. And as I told you before, if you want to draw this line through there till you hit the curve, take the projection down here, you can get a safety factor. Safety factor here might be about 50%. So go back and redo it by raising the stress to 85. Keep everything else the same. Since the yield strength is 100, then the stress ratio is 0.85. The K ratio, well, get a new K applied because you have a higher stress. The applied K is 106 and the K ratio is 0.888. So go back to this curve, and 0.85 and 0.888 is about here. It's outside. So notice in this analysis, this is not yielded yet. This is not the K1C yet, but by the R6 analysis, you're outside of the curve, and so that would predict a failure, being outside that curve. Some other methods that are similar, and these are British standards, was originally PD, which I don't know what it stands for, had a PD number. Now it's BSI. So this stands for British Standards Institute. The British Standards Institute is a little bit like ASTM or ASME. They kind of lump the two together. ASTM or ASME in the United States, this is in Britain. So they do flaw assessment methodology with 3 levels of assessment. Let's see if I have the picture. Level 1. Level 1 is just a square box. K has to be below 0.707 of K1C, or stress has to be below 80% of the yield. If you have those two things, level 1 is secured. If you don't secure level 1, you go to level 2, and their level 2 is the R6 diagram. So the R6 method is level 2. Now, for level 3, you have to have a material specific curve. It's down here. People who develop these kind of material specific curves don't tell you how they do it. They just do it and say, here it is, you believe it, you should believe it. So this is similar to an R6, but notice it goes beyond stress limit of 1. This is actually a stress limit. L sub R is a load limit, load to a yield load. So this is based on stresses here. This is more based on loads, and the load limit of 1 is a kind of a limit load. The K ratio, though, is K to K1C, and if you do the analysis and start with level 1 and your level 1 doesn't make, then you try level 2, and if level 2 doesn't make, you try level 3, and if level 3 doesn't make, you give up. So that's these kind of things. The idea for all these are what we call cookbook. I don't know if you're familiar with the term cookbook. You follow a recipe to cook your whatever you cook at home. Step 1, step 2, step 3. Same thing here. They like to have step 1, step 2, step 3. You just go through step 1, step 2, step 3, and follow down the line, and then you don't need to know too much fracture mechanics. So you have to know just enough to calculate stresses and that kind of thing. So those are 2 failure analysis diagram methods. Talk a little bit about the fracture mechanics code from ASME. We mentioned that, I think, last week about section 3 construction rules and section 11. This should be 11 instead of 9, but section 11 is inspection rules, and they use these reference curves that we talked about. One of the problems with these reference curves, and again, one is a reference for K1C data. Those are tests run by E399 and get a valid K1C number, and then the KR ratio are things that are run by other standards or no standard at all, dynamic or crack arrest or something like that, and then lower bound curves were drawn, and a exponential was was written for that. The abscissa here, the thing that sort of centers that is called RT-NDT. It's based on NDT, which is called nil ductility temperature. I don't know if you all know how to do that. I mentioned that was done by taking a specimen that has a weld bead. The weld bead is given a little notch in it, and then it's set in a fixture, and a big weight is put up maybe 10 or 12 feet in the air and let to drop freely and whack the specimen. And they see if it breaks or not that way. Now the problem here is this is really not a fracture mechanics type test value. So fracture mechanics data here are put together with non-fracture mechanics data, and this is ASME code, and people were thinking that doesn't make good sense, and they wanted to change it. So the idea was to use the T0 as a reference rather than the RT-NDT. T0 came from the transition fracture toughness testing, and the Weibull statistics that we talked about yesterday, that was where the T0 came from. And so if you base that on the master curve technology for transition fracture, you would have then a median curve, and they like the idea of lower bounds. So they took the median curve and shifted it by 30 degrees Fahrenheit to get a lower bound concept. So here's how you did, remember, the master curve from tests arranged in a Weibull statistical way, and then the median is drawn here. And so shifting it by 35 degrees and using T0 as the reference pretty much lower bounds all this. Now whenever you do a bunch of tests, and this must have hundreds of tests in this set, you don't always get everything being safe. There's a couple things fall outside the lower bound, but in general that lower bounds all these data. So they were hoping then for ASME standards, don't do this. Don't do the K1C, K1R based on these equations. Do it based on master curve. Now, as far as I know, they are still working on it. I haven't heard that came out in the ASME handbook. And in ASTM, when we wrote test standards, it took us about 10 years. As far as I know, they've been working on this for a long time. Here you can see 1996. And this person, Michael Sokoloff, works at Oak Ridge National Laboratory, so he's really a neighbor of mine in Tennessee, and he does fracture mechanics at Oak Ridge National Laboratory. First idea came up 20 years ago. So it seems to me that in 20 years they still didn't manage to get it, but that was the idea of putting that in. Now I wanted to talk about some of these, but I have these in a different set of curves. I'll see if I can find that. All these things are not in necessarily great order, but talk about this. New trends in standards and software. So that kind of follows with what I was doing there, and talk about software and other things. Lately, at least, and lately being the last 20 to 30 years, a lot of fracture mechanics projects end with the development of a software package to do the modeling. Or they develop procedures that are written down in cookbook style. The type that's used where you don't have to be an expert in fracture fatigue, but you just follow the rules, step 1, step 2, step 3. For my approach, I like software and cookbook approaches if you know what you're doing. If you don't have a basic understanding of what you're doing, in a software package you can make a small error in some input and get an answer that's nonsense, and if you get that answer that's nonsense, you might not know the difference. So I like to see it I like to see it put into well, people who know what they're doing. Now, since the development of the European Union, they've funded a lot of projects related to fracture, and most of these projects have many different countries involved, maybe up to about 10 or 12 countries involved, and usually it's centered at some place. Now, a lot of these developments were centered in Germany at a lab that I worked at for a year. I took a year off from teaching at University of Tennessee back about 15 years ago and worked at this lab, and they were working on these methodologies, and they are then given an acronym. FitNet is fitness for service, and it came out from a project, a 4-year project, and there's a website that you can get to it. Now, when they finished that, they decided to go ahead and make it better, and they developed something called SYNTAP, Structural Integrity Assessment. Normally when you do these kind of things, the idea is to come up with an acronym that is catchy so people remember it. This is a structural integrity procedure involving fracture mechanics. Again, pretty much of a procedure that allows you to not be a real expert, and these are both on the internet. However, I don't think they're free. I think you have to pay if you're not a member of European Union. Of course, we're not in the United States. I suppose you're not here in India either. That's European Union is all the European countries that do this kind of work. So these are the European methodologies. But if you need a methodology, I think they're pretty good, especially the second one is the most recently developed one from Europe. Here are some other software packages, and I have never used these, I just know that they exist. AFGRO is a fracture mechanics program, and as it says here, all the information you need to know to use it is in the website. NASGRO analyzes fatigue and fracture, and also does finite element analysis, I think, of structural life, and it's good for airframe. Now, NASGRO is from NASA. That's a U.S. government agency. U.S. government developed projects have to be free to people, so this is something you could use freely. Here's one. I don't know anything about that one. Just wanted to mention some of them. So talk about NASGRO. NASGRO is fracture and fatigue analysis software. You can analyze fatigue crack growth and fracture. You can do structural life assessment. You can do finite element analysis within that. They have fatigue and crack growth properties in that, and they can analyze the initiation as well. So here's some words about NASGRO. It was developed at Johnson Space Center. That's in Houston, Texas, in the United States. That's a center that they used to use for controlling space programs like moon rocket shots and things like that. The NASA launching area is in Florida. So most of the launches are in Florida, but once they get the thing launched, then they monitor it in Houston. if you ever get to these cities, you can go tour these kind of things. The launching site, I've toured that, and I've toured the Johnson site. The launching site is Cape Canaveral, or sometimes named after Kennedy. I think they switch back and forth, and that's in Florida, on the east coast of Florida, near the Atlantic Ocean. And this one then is in Houston, Texas, on Gulf of Mexico, and they also have a visitor center, and you can go see all the rockets and everything if you ever get down there. So they started in 2000 to develop this software, and they redid it 3 times. So the third cycle was done about not quite 10 years ago. So it's available, as I said, and since it's done by a U.S. government agency, it has to be free to users. One of the things that was complained about this, or people weren't real happy, was originally, at least, it was all linear elastic, so only K solutions and no J's or CTODs. And people were interested then to go beyond just the K solutions. And I don't know if they've gotten that far yet, but I think they haven't. Now, the petrochemical chemical companies, oil companies like to use the CTOD, and they pretty much follow the British standards in developing their stuff. There is a thing, American Petroleum Institute, API 579-1, and now is also an ASME standard, and they have fitness for standard for pressure containing equipment in refining petrochemical industries. So this has been used a lot in petrochemical industry. It's primarily based on Ks and CTODs, and it was first issued in 2000. I think it is modeled after British standards, and it's also cookbook in nature. I think certain people involved with ASME give short courses on how to use this, and the whole course is devoted to using something like this. So it's something that people use. Here's some words about that. American Petroleum Institute is a big institute, and they have this practice for pressurized equipment used in oil, gas, petrochemical industries, and the last edition that I saw was 2007. When I worked at Westinghouse, occasionally we got together with petrochemical people and tried to talk about mutual problems, and that never worked out. The petrochemical industry is really competitive, and so they keep a lot of their stuff secret. So if you want to go talk to them about what they're doing, they won't tell you. We're doing something good, and don't worry about it. It's safe. And we had a different attitude at Westinghouse. When we developed the technology for power generation industries, we always published and shared it with other industries, but not so much here. So you can purchase this. $650 was, I found this online. I never purchased it for this one, which is by CD, and if you want a hard copy, $775, and I don't know what this one does, but $1,000 is 66,000. This is about 70,000 rupees, Indian rupees. So I don't know. Most people don't have that in their pocket. Do your institutes have that much money to spend on this kind of thing? No. But as I said, some of these things are free, so you can get them from, you can get them and use them. Since a lot of you were asking about concrete stuff, and I wasn't an expert in that. I looked up some stuff on concrete and wrote a little bit. Now this is kind of scattered, just things that I found here and there, but give you some of the people who are actively doing stuff on concrete and fracture. So as you know, some of these problems in concrete are the materials not homogeneous. Concrete has a matrix material and then aggregate particles. Aggregate particles can be big or little. One thing you could do is ignore this fact that it's not homogeneous. Another is to do something special to take care of the non-homogeneous character of this. So, thought I would show you that things are still going on. I mentioned ICF, the ICF session, ICF International Conference on Fracture. This is the one that's going to be held in Greece in 2017, in the summer of 2017. And there was only one session that I saw for concrete. Now this is 1 out of 66 sessions. The people, I don't know any of these people. These are the people that are organizing it, and looks like a good thing, but it's only one session. As I said, it's not many sessions. And one of the things that was a little surprising, in their session they had 11 topics that they and I didn't write them all, but 11 topics that you could present a paper on. And these 11 topics are for one special session, and as I said, special sessions were 1 out of 66. So I don't know, any of you have money to go traveling to conferences like this? If you want to go to a fracture conference, ICF 14 is the #1 fracture conference in the world. So it's not specific to any country, US or Europe or anything, but I'll show you later. It's been held all over the world except Africa. I don't think it's ever been in Africa, but started in Asia. It's been in US, it's been in Canada, it's been in Australia, been in Europe. So it's been around, and now number 14 of this is going to be in Greece. And these are the topics then. I just wrote a couple of them down out of 11. Recent advances in fracture mechanics for concrete, experimental and computational methods, and then 3, 4, 5 up to 10, interface, debonding phenomenon, brick masonry, concrete like quasi-brittle material. So a lot of stuff for concrete, and this is a chance then to get the concrete people together. Now I showed you, well, I don't think I showed yet, but I'm going to show you 2 sessions in composite materials. Now, found on the internet, fracture mechanics for structural concrete, and the author didn't put his name down. It just has this lecture, and he talks about introduction, why do you need to consider fracture mechanics for concrete, and then computational models. And these are give some interesting things. So crack tip zones. In linear elastic fracture mechanics, you get high stresses near the crack tip, and if you approach the crack tip itself, the elastic stress is infinite. So because you can't develop infinite stress in real materials, you get something happening. You get an inelastic zone, and in metals then you get a plastic zone. So at the top crack tip, metals develop plastic zones. In concretes though, this high stress near a crack tip develops what they call a process zone consisting of many microcracks. So instead of yielding, which concrete I guess doesn't do, you get a whole zone of micro cracking, and that micro cracking around the crack tip then has this. Micro cracks, cohesive pressure still exists. This all I copied from that website. It's all nonlinear, has finite tensile strength, and has a big size. So in contrast to metals, where as you get yielding in metals, you usually get hardening, and strain hardening means that as you get more and more strain, the stress goes up, like a power law. But in concrete, it says you get strain softening. So in this, it talks about testing a little bit, a test load versus displacement. Usually in concrete, you start with real linear elastic behavior. After a certain load, it becomes nonlinear as microcracking develops, and then after a while, you get maximum load that represents failure. Here's a kind of schematic. Linear elastic region, then the microcracking, and this doesn't give you a nice smooth curve like you might get with metals, but just sort of a jaggedy curve, and then you get a maximum load and the thing fails. So those three regions are dominant in this. So fracture analysis in concrete. Concrete analysis is generally based on energy criterion. I think I saw some people doing K analysis, but I can't remember where. So if aggregate particles are really small, then perhaps homogeneity is not a bad assumption, but in general the homogeneity doesn't work and the K analysis doesn't work, but more often you have energy analysis. So here was an energy equation that came in that, and like metals, then it has the G from Griffiths, which is energy to create new surface. Now in the metals, the total energy and this energy are the same, but in the concrete, then there's a second integral that's added to that, and that integral is energy to separate surfaces completely. So I guess surfaces start to separate, but then there's some cohesion between them so they don't separate completely. Now, some of the things that people do, here I found this fella is from United States, works at Northwestern University, which is near Chicago, Illinois, and he had this form, stress based on tensile strength, tau, and square root everything is under the radical there of these terms: specimen size, some constant lambda, and then aggregate size. So the whole critical stress is influenced by aggregate size. So the bigger the aggregate, I guess, the smaller than or the lower the critical stress. So that's his. Now, in fracture mechanics, critical stress is a material property, but in concrete, the critical stress has other things that come in, like aggregate size comes into that. So it's not just material property, but it's a material property plus other things. And it's a size-dependent parameter. Here are some of the people then. That guy who developed his relation, size relation, is this fella. I thought it'd be interesting if you want to know some of the people involved. These people are mostly old people, and I thought I was old people, but these people are older than me. He was born in 1937, so he's getting close to being 80 years old. and I don't know if he's still working, but in the web page he seemed to be still working at Northwestern University. I've known some professors at Northwestern work into their 90s, and they just love working at the university, so they keep working there. Here's a Russian-born one. I don't know if you ever heard of him, Barenblatt. He's still living. He's born in 1927, so he's about almost 90 years old. I've seen him at some conferences. He is very confident and full of his own self when he gives a talk. Have you seen him? He tells how wonderful he is. So if you don't believe that he's really great, you could ask him and he would tell you. But he developed this cohesive zone model that's used in concrete in 1960s, and recently, since about the year 2000, it's used in metals as well. This cohesive zone model lends itself very well to numerical work. And a bunch of people I knew doing numerical work were just working on cohesive zone model all the time. So fracture formation is regarded as a phenomenon in which separation of surfaces are involved, and then you can do finite element analysis near the crack tip, calculate stresses, and then calculate what causes failures, and try to relate it to real material behavior. Lately, people doing numerical modeling seem to not regard experimental results. If you are an experimentalist and somebody does numerical modeling that doesn't fit your experiment, you say that their numerical model isn't correct. And if the people are numerical people and your experiment doesn't fit theirs, they say your experiment's not correct. So it depends on which side you look at. I tend to believe the experiment. You do a test and something breaks at X load. If the finite element model doesn't predict that it would break there, I would think that's wrong. So I think that's a little backwards. So just a Barenblatt model. That's used in concrete. Here's another model I found used in concrete, the Dugdale model. Now we just did Dugdale as basis of the R6 diagram, so he got around a lot. He was British, and I never met him. I think he was of an earlier generation, so I think he's no longer living, but he had a model in which a plastic zone is near the crack tip and equal to the yield strength, and his model, as far as I knew, was always applied to metals, things that yield and don't microcrack. However, seems to me that his model is used in concrete as well. Here's another one, Hillerborg. This was proposed in 1976. It was the first model to analyze concrete using fracture energy. He had two crack regions, the physical crack and a fictitious crack, called fracture process zone. This sounds a little bit like what we talked about yesterday, the idea of Irwin of extending the actual physical crack by a fictitious crack to get a new value of K. So this has a little bit of that in it. Now if you want to do finite element work in concrete, I found this, and I don't know too much about finite element work in concrete, but it said if you look at mesh size and vary it, you get different results depending on what mesh size you pick. So if the mesh size is higher or bigger, I guess, then structure seems to withstand more stress. But these results obtained by the finite element analysis contradict the real case. So I guess the finite element analysis and the experimental results don't agree here. And that's well, that's the way it is. So that's a little bit, I think, of an overview of concrete. So since some of you are working on concrete, you have discussions or things more on concrete? The thing I was going to point out, I guess, this model, this model and this model are not new. So I don't know what's new is in that. If you want to find out what's new, maybe you could go to the ICF 14 and see what they're doing. But seems like concrete work is not a real major thing, but people are kind of working on it over the years, developing models and doing this and that on the model over the years. So it's not ignored. However, from my point of view, where I was involved with metals, working in metals and working in concrete seemed to be two different groups of people that never met. You find the same thing? Yeah, just two different groups, and we never got together. Which well, the concrete are going to have a session at ICF 14, but as I'll tell you, the work in a big conference like that is usually nobody pays attention to anybody else's stuff. We should take a break now because number one, the time is 1 hour. Number two, I think I see tea out there. So if you want to take a tea break, you can take a tea break with actual tea, which is the idea of the tea break, that you have tea. He was just talking to you about the exam for tomorrow, and I was going to say a few things, maybe help. It should be pretty easy. Sometimes what's easy for me isn't easy for everybody else, but you never know. Anyway, let me say a few things about it. As he said, it's open everything you can think of. You can bring, if your children know fracture mechanics better than you do, you can bring them, or your grandparents, whatever, but I recommend not. It's largely based on the first week. There will be, I was going to have 4 writing problems where you have to figure things out, but it ended up with 5 because I got rid of one and it came back while I wasn't looking. I don't know if you ever do that. You write something out and then you throw something away and it just comes right back again in the middle of the night. So there are 5 problems. We're going to let you pick 4 or 5. So that's 60% of the exam, 4 or 5 problems. And then the rest are short answers. The problems are all based on linear elastic fracture mechanics. The short answers have some of this first week and some second week stuff. And I wrote it so long ago that I can't remember what's all on the short answer problems. But I hope it's stuff that I could do if it were up to me to take it. But this was my review yesterday. So some things you should definitely know. How to get K's from your tables. And by the way, you should have something to calculate, like a calculator, because you'll need that for working the problems. How to get the K's are important. You should know the basics of the K1C test. That's lecture 3 or so. You should know the basics of the ADN delta K fatigue. I don't think there's anything on stress life problems, but the ADN delta K problems. You should know, I don't think there's anything on this. You should know applications, how to get critical crack sizes, how to get cyclic life. You should know the fracture mechanics triangle so that if you know 2 things, you can predict the third. Like if you're given the stress and the material property like K1C, get critical defect size, stuff like that. So that's. And any question about the exam and what's on it? So everything is open but your mind. You should have a open book, open computer, open whatever, closed mind. Nothing worse than when I gave an exam at University of Tennessee and I had 90 students and I give them a problem and I get 90 different answers. That's not good at all. We just went over some of those weird nonlinear fracture mechanics applications. I wanted to take a few of them and show that you can actually use them and do stuff with them. So this is just a short workshop to do some stuff on that. Talked a little bit about CTOD design curve. And the main thing about that is getting critical crack size. So here's how you would do it. Here's the problem. There's a hole in the plate. If you have infinite plate, stress concentration is usually 3. So that's just the standard solution. So now this has a membrane stress of 350 MPa and a residual stress of half the yield strength, no bending stress. The yield strength is 600. The modulus is 210 GPAs. And then yesterday we did critical CTOD from that CTOD test and got this in inches, but I'm doing this in SI, so I converted that to millimeters. 0.1 millimeters of CTOD critical is pretty big. If it's a really brittle, low toughness case, it would be smaller. In a lot of cases, it's not too much bigger. But so all these things you have to remember: membrane stress 350, residual stress half the yield, yield strength 600, modulus 210, and this is critical CTOD. So here are the CTOD design curve equations. This came out to be a little small. So stress concentration times membrane and bending stress plus residual stress or secondary stress, all divided by modulus to get the strain. And then use this. Okay, so here's the strain. KT is 3, membrane stress is 350, half the yield is a half times 600, divide that by 210 and get 0.00643. That's a pretty high strain. The yield strain is 0.00286. So when you put that together, you get strain to yield strain of about 2.25. Now the graph is a little hard to read, but it's like this. 2.25 is here. You come up here and you get this phi factor of 2. See if I can convince you. 2.25 is about 2. This is what the phi factor is. This is the vertical, the coordinate on that graph is delta critical 2 pi yield strain crack size. So to get critical crack size from that, put in CTOD critical, then 2 pi yield strain, phi, this is phi 2 pi yield strain. So you get a critical crack size of 3.1 millimeters. And that's what this whole thing is designed for, to get critical crack sizes. So that's one problem. Now, thought I'd show you one of these. This is the newest thing from England, and part of their upside down look at fracture behavior. I want to do the above problem, but no hull and no residual stress. Here's the applied stress. Here's the yield stress. I'm going to use a center crack model with A of 3.1. So I took it from here, 3.1, and K1C didn't have it on the previous problem, but that's 80. So CT center crack model, I'm going to use the infinite plate model, which then has capital F of 1. So sigma squared of pi A times capital F, which is 1, 350 for the stress, square root of pi A, and don't forget this when you're working with SI units. It's best for K to put everything in meganewtons and meters. Meganewtons are MPAs and meters. So this is MPAs. I put this into meters, not millimeters. Again, the problem with millimeters is if you take a square root of 1,000, you don't get a decade. You get 30 something or other. So if you get the wrong units in there, it messes up easily. So here, meters, MPA, so that you get MPA root meters. So the SR is 350 over 600 is 0.58. The K ratio is 34.5 over 80 is 0.43. Here is this. This is level 1. You have to be less than 0.707 and less than 0.8. So if you fit in here, you're okay. So I'm safe at level 1. I didn't put the point there, but 0.43 and 0.58 puts me about here. So somewhere right in, easily safe, and almost the safety factor of 2 there. It's very safe. Now, in order to expand your knowledge a little bit, I changed the stress and the crack size. So we do a new problem. So stress of 450 instead of 350, doubled the crack size, and then get a K of 62.8. The stress ratio is 0.75. So 0.75 is inside here, it's okay. The K ratio is 0.785. You're supposed to stick with 0.707. It's not okay. So the point is somewhere up here. It looks like it's going to be within in the level 2. But in order to tell, here's the level 2 equation. And that's the equation of this curve. If you look back in the previous lecture, you can see that's the equation of that curve. Now, I want to go this way. So stress ratio 0.75. The graphical point has a K ratio of 0.85, and it's less than this value here, which for level 2, when K is 0.85, K was 68.8. Okay, so, well, let me show you. The point is right up here, and it's safe, and it's safe by this curve. But this is what you could do with it. You can take this K ratio and get a critical crack size from the K by letting A be the unknown here. So this is this is what you would get as critical crack size for level 2. And I don't have the level 3 equations. I don't know how to do level 3 here, so I don't have those level 3 equations, and I can't, so I didn't do an example. So, but if you miss here and go outside here, you can try level 3, and if level 3 works, that's good. Here is, well, that's R6 diagram. Okay. Questions on that? You won't have anything like that on the exam. That's too much trouble. If you're interested in research from purely fracture mechanics point of view, a lot of the work is featured in journals. Here are some of the journals and their publishers, and many libraries and universities collect these. Let's see. I'm on editorial boards on some of these. So editorial board means you don't get any credit for anything, but you get a lot of papers to review. So I do for these two. Engineering Fracture Mechanics was started by Paul Paris, and is, I don't know how many years old, but there's a lot of papers come into that from Asia, Europe, fewer from the US than it used to be, but Asia and Europe seem to be the center now of that. Fatigue and Fracture of Engineering Materials and Structures was started in Great Britain, and that's that. Now there's some others that do fracture. International Journal of Fracture, International Journal of Fatigue and Fracture. These are mostly metal-based, but not necessarily. One of the things that's not completely fracture mechanics is the ASTM Journal of Testing and Evaluation. Test methods are in that, new test methods. If I was developing something new in the test method field, I usually publish there, otherwise here. And I think one of the things the journals like to do is look for impact factor. I don't know if you know the impact factor. This one probably has the highest impact factor. And I don't know, do you know how they calculate that? I knew once, but impact factor calculation is something that's easy to forget. So if somebody tells you how to do it, about 5 minutes later you probably forget how to do it. Nevertheless, they all run around showing their impact factors, and this one has a pretty high one. Oh, I did write some things about it. Here are where most of the papers come from Asia. If you want to publish in some of these journals, for example, Engineering Fracture Mechanics, I think they said more than half the papers are rejected. So there's a high rejection factor. One of the reasons for high impact factor is a lot of rejection. So a lot of papers are rejected, and almost every paper that I review requires some revision. So usually have to revise the paper. If people are not native English speakers, which happens a lot of places, then sometimes the English writing isn't good. Now I wanted to tell you about research found in conferences and symposia, and one of them is the ICF. I'll say more about that. ASTM has a national symposium on fatigue and fracture mechanics, and it started in the 1960s, so it's up to number 40 now. And recently, ASTM, which is American Society for Testing and Materials, got together which with ESIS, which is European Society of something. It's a European Society of Fracture, and they went together to do this symposium. And there's one coming up next year, the 40th one of that. Now, if you have an email address, which is sometimes is good or sometimes bad, about every other day I get a list of some conference coming up and invite to give a paper. Now, if you do it every other day, that's about 180 invitations a year. It's hard to write 180 papers in a year, and so you have to ignore that. I don't know if you see this. A lot of, not all fracture, but related to that, are being given in Kuala Lumpur and Singapore. You ever see some of those? They come a lot, and I don't know who organizes those, but they must have a conference every week there. So I wanted to talk about International Conference on Fracture. I told you that's the #1 worldwide conference. It's held all over the world in 5 continents that I could count, and once 1984 was in New Delhi. Now, I guess New Delhi is the state and Delhi's the capital city. Is that correct? I didn't know that until maybe a day ago or 2 days ago. Anyway, I don't know what city that would have been. Would that have been in Delhi? Anybody around in 1984? That's over 30 years ago. So it's the first conference was 1965 by Yokobori. It was ICF 1 in Sendai, Japan. Believe it or not, 1965, I was a student yet at Lehigh, and I couldn't go to that because I was a student. In fact, I've never been to ICF because something always comes up that doesn't work for me to go. Anyway, it's held every 4 years. That's why this is 50 years ago. In 50 years, there's only 14 conferences because it's held every 4 years. So the next one is in Rhodes. And when I wrote this, I looked online for ICF 14. There were 68 special topics, plus 4 honor and memory sessions. Now, last time I looked, that was only 66. So some people must have withdrawn. Nevertheless, 60, and these usually take place in about 3 days, means that there are 20 a day. And when there's so many in a day, nobody goes to anything except the one they have a paper in. So it's a little bit bad. I think it's a little much. But there's a lot of topics, and you can look at this web page and see them. Here's some of the topics. And I didn't know what you were interested in at the time, so I just wrote some that I found. Fracture and fatigue in aggressive environment, that's still of interest. Fracture and material forming. Mixed mode fracture, which I told you people get interested in mixed mode fracture every 15 years or so. So that's come up again. Additive manufacturing. Additive manufacturing is one of the big topics these days. And 3D printing. I don't know if you get 3D printing here. Yeah, we had in Oak Ridge National Lab, they printed a whole car with 3D printing. Not the engine, I think. I asked them about whether it's the engine, but the body of the car. And I was over there about a month ago, and that was one of the things they're proud to show. I saw the car, so it looks like a real car, and they can drive it because they put an engine in, but they said they don't drive it a lot because they're afraid it's going to fall apart. So 3D printing of cars probably isn't going to catch on right away. I think the car manufacturers still use the old-fashioned way. Here's some gas pipelines. I don't know, how's the gas industry here? We've discovered a lot of new gas in the United States, and gas is one of the primary energy generating things. So coal, we used coal for many years. Coal is a big pollutant, and they wanted to phase out coal. Now, I'm afraid with Trump, he will bring it back in because he likes to do things that aren't good. So he's going to bring coal back again. But gas had been the main thing that people were putting up besides renewable energies like wind and solar. Okay, here I have one in multi-scale fracture of concrete, rock, concrete, and aggregates. Quite a while ago, but not all that while ago. While I was at University of Tennessee, I started working with a geology student who was doing a PhD, and he used fracture mechanics to look at fracture of rock during the formation of the mountains. As you know, mountains are formed by plates bumping against another plate. Are the Himalayas still rising? So that kind of thing sort of rises, and if they get a flat layer of rock and something pushes against it, it starts to fold, and as it folds, it starts to crack. So he used fracture mechanics to talk about the cracking, and the loading is a little bit slow. Said you go from this to this in maybe 500 million years. So it's not something you could stand around and watch happen, but it happened. And that was interesting. Get some interesting things. The fact that you could use fracture mechanics with rocks and look at it in terms of geological formations. Here's optical techniques and its application to fracture mechanics. So on new topics, the best way to get an idea of what's going on in new topics is just to look around and see what comes and what's coming. Okay. Here's one thing that I thought I'd show you if I have the time, which we do, which is creep and creep cracking. This is high temperature problems. So in listing the behaviors of different things, one of the things that people do, well, fracture toughness, fatigue, environmentally enhanced cracking, and then at high temperature, creep and creep cracking. So talk about creep. Creep is a time-dependent deformation process occurring at elevated temperature. I'll talk about just general creep for a little bit and then creep cracking. At a constant stress, displacement occurs as a function of time. So normally in a creep test, they hang a constant load on a specimen, and it may be enhanced by a lever system, and then that thing starts to deform or displace continually. Creep is said to happen at any temperature more than 50% of the melting temperature in degrees Kelvin, so absolute temperature. Now that's a rule, what they call just a general rule, but it's not necessarily true because I've seen creep at lower temperatures if you have enough time. At higher temperatures, the creep happens pretty quickly. Pretty quickly, maybe 1,000 hours or so. So if you have a constant displacement and you creep, then you get stress relaxation. So constant stress, you get stretching, constant displacement, hold it there, the stress relaxes. Here's the creep deformation curve. When you load a specimen, it gets a stress right away, or a strain right away, sorry, that's a strain versus time, and then starts to deform and has three regions. One is called primary, secondary, and tertiary. It means region 1, 2, 3. In this region, the creep rate starts pretty high and slows down. In the second region, the creep rate is almost constant, and in the third region, creep rate increases. And in this region, then with creep rate increasing, you start to get things happening like voids opening up so that you're losing material, and then eventually goes off to failure. In the region 2, where you get a constant thing, these are log plots. Constant rate is where people do most of the analysis. They call that the steady state, region 2 or steady state region. The creep rate is constant at a fixed stress, and the relation between creep stress and creep rate is an analogy to plasticity. So here's the analogy. Creep rate is constant. The creep rate can be calculated through a power law. So the dot on top of that means the derivative with respect to time. That's I guess that's a general mathematics symbol, that you put a dot on top of a thing, meaning you take the first derivative with respect to time. So a coefficient times stress to an exponent is what you do for creep rate in region 2. Now, one of the things in creep is the stress life. The creep life depends on temperature and stress. So temperature and time can be combined through a Larson-Miller parameter. And the Larson-Miller parameter is like this. This is time to failure. This is base 10 log. That's temperature, and that's a constant. For metals, people use 20, but for other materials, 20 doesn't always work. So normally you have to figure out what constant C works. Anyway, the Larson-Miller parameter for creep life can do this. Here's a bunch of creep life curves at different temperatures. So here, this is iron-based alloy. So I don't know where iron melts, but you do get some creep at around 600 degrees Celsius. So this is rupture time versus applied stress. Applied stress is usually applied load. So if you get necking or anything, they don't take that into account. They just take the initial stress. Each point here then would be a different test. So they put the test in a creep fixture, again, which has a constant load applied to it, usually through a lever to increase the load from the load pan, and then you measure the time it takes to fail. And of course, at higher temperatures, it takes less time to fail than it does at lower temperatures. Or at higher temperatures, for the same rupture time, you need a much lower stress. I don't know what the yield strength on this is. Didn't see that. Anyway, this is a log plot. So tests here go from, this is at 1 hour. These tests would be just short time. And way out here, 10,000 hours is a little more than a year. So some of these tests fail almost as immediately when you put the load together. Others go for about a year. People could test at longer times than a year, but they don't usually because they run out of patience. If you don't get a result within a year, you can't publish anything, and then you lose your job. So you don't want too long a test. And I told you how nature doesn't like long tests, but this doesn't matter. It doesn't have any electrical thing in it other than maybe the data acquisition system. Creep rupture, usually put on the stress or the load, sit and wait for it to fail. And all you need on that is some kind of clock. Anyway, if you go back to this Larson-Miller thing, using C of 20 log base 10 of time and get a Larson-Miller parameter, then all those tests, these are all the tests from here, all those tests fall into a single curve. Nice thing about that is that kind of organizes the result in a way that you think is good. When you see a whole bunch of scatter like that organized into one single curve, it's a good thing. Now, people been doing creep rupture tests for years and years, and that's one of the design things people worry about. High temperature applications, particularly like gas turbine engines, airplanes have to worry about that. In former life, was still part of this life, but it was so long ago I forgot about it. I worked at an airplane engine place called Pratt & Whitney. Pratt & Whitney is one of the big airplane engine manufacturers in the United States, and I worked there for a while in a materials lab, and we did a lot of creep tests there. But creep cracking is this. You get slow, stable crack extension under constant load or with increasing displacement at an elevated temperature. This is a little bit like environmentally enhanced cracking, only the environmentally enhanced cracking that we looked at was pretty fast. We said if you get above the threshold, then you would normally have failure in a short time, usually hours or days at the most. Creep cracking has an analogy to plasticity because of the power law relationship in steady state region 2. So that was a help in creep cracking. Now, creep cracking parameter was developed, which is analogous to the J integral. This is exactly like the J integral, except this is called C star parameter. The strain energy density is replaced by strain energy density rate. So this epsilon then has time dependent, or is a time derivative. The U dot, the U, which was a displacement vector in the J, is replaced by the derivative. So all the displacements and strains have time derivatives instead of just the actual value. Another parameter that's similar was developed called the CT parameter, and it is an energy rate rather than an energy time derivative with crack length. This is like the J, except that again all the strains and displacements have time derivatives in them. Since there's an analogy to plasticity, the C star is often calculated using the J handbook. And you can use it from the J handbook by just using this power law which goes into the J handbook, but putting time derivative where you would have just strain in that. So here's the an equation. You don't need to do that, but there's an equation that's easy to generate. Here's some data, and what's done then, crack growth rate is measured as a function of either C star or CT. So this is a case where it's measured as a function of C star. The ADT here is an inch per second. Not real good, but it's fairly slow. So it takes some while to do these tests. Here is a compact specimen and a center crack specimen. If you can get the things to line up for the two and come together, then the parameter seems to be pretty good. Here's another one, and this is using the CT parameter. Might point out the material here, this is a stainless steel, 304 stainless steel. Is somewhat of a high temperature alloy. And 304 stainless steel is austenitic. It usually has about 18% chrome in it and 12 nickel, something like that. This material is plain steel, but this is a high temperature steel. This is the kind of steel that we used in high temperature steam turbines at Westinghouse. So you can see again, compact and center crack. You get a almost like fatigue straight line when you use log-log plots. Not exactly, but almost like that. Here's another one, same steel using C star. There is a technology for doing analysis. Back when we first started doing creep cracking, people were saying that creep exists only in stress rupture, only in tensile loading and no cracking at all. And then one day a big pipe burst at a place in California where they had some kind of big steam pipe, and the pipe burst by having a crack that went for feet or meters, several meters long. And when it went and broke, steam came out and unfortunately hit many people, and I think up to 6 people were killed by that. And after that, then they said, oh, you do get cracking after all. It's not just tensile behavior. So people started to believe in creep cracking. And here is a creep problem in a pipe that you can use this technology to do the analysis of life. So here's the pipe. It has 2 ends. This is a pipe that would be on a steam generator, usually at a pretty high temperature, 600 F or C or more, but it has a hot end where the steam comes in and a cold end where it has, I guess the steam is cooled down already. The hot end has some damage to it, and the cold end has no creep damage to start, but you want to estimate life. This is a pipe wall. It's not a center crack specimen, but a pipe wall. Has this little internal crack in it, and you can't read these things because this didn't come out high enough. But anyway, the stress is PR over T. I don't know if you know that. If you ever do pressure vessel stress, PR over T. The pressure was 600 PSI. The radius of the pipe 15 inches, and wall thickness 1 1/4 inch. Stress came out to be 7 KSI. 7 KSI would be about 50 MPAs. So not a real high stress. The material was operating at 1000 F, and it's 1 1/4 chrome, half moly. This class of steels is always used at high temperature, chrome moly steel. Here are some of the data in that D80T versus CT, and there's two sets of data. One is for the cold end, where you didn't have any prior damage, and the other is for the hot end. So the hot end has faster rate than the cold end, as you would expect, and doesn't look like much difference, but remember this is a log scale, so the difference between these two curves is at least a factor of 2. In order to do the modeling, you need to do, well, you need to get the creep rate equation in region 2. And again, here is the power law, creep rate versus stress to a power. And the hot end is here and the cold end is there. Again, it doesn't look like much difference, but if you take a vertical line here on a log plot, it's a pretty much, I think, a factor of about 10 difference down here. Up here, not so much, but down here, a factor of 10 difference. Here's how the life is predicted. The hot end properties, that would be these sets and these sets, the hot end properties were used to calculate life using the D80T. Now this is not life exactly, but crack length versus time, and when the crack length gets real high, then they say end of life. At the high temperature, there was no real failure criteria, no K1C, no J1C for this material. So they just did the analysis until the rate started to go really fast, and they said that's end of life. So you can see here time in hours. Here is, see, 10,000 hours would be here. So this is about 10,000 hours. Here is about 100,000 hours. 100,000 hours would be a little bit more than 12 years. So they're predicting life. 10-year life prediction isn't too bad. But if you use just hot end material properties, you don't get much more than a year of life. And if you use plain old cold end, here's just the cold end properties. If you use plain old cold end, the life is much longer, 200,000 hours, which would be some almost 25 years. Now what also did, using cold end properties, all of a sudden get here and switch to hot end properties to see how that affected things, and of course that went off to failure really quick. So those are the failure things in that. Now, creep cracking has ASTM standard that was developed in 2007, and it's standard method for measure of creep rate times in metals. One of the bigger problems is creep fatigue, and there's a standard that was developed just a few years ago. It's the latest thing I found. Notice the ASTM numbers are chronological, like K1C is E399. This is E2714. So that's how many mechanical test standards have been written as of this time. One of the good things about that is when people write a standard, they get tired of it after a while and it gets thrown away and new ones come. But this is the latest creep fatigue standard. That's the story in creep and fatigue. So I think That was all I had prepared for today. I was supposed to go 3 hours, but I go 2 hours instead because that's all I had prepared. I don't know if you want to talk about anything else. We could take time to discuss things. So tomorrow we'll talk about things. If you want, tomorrow could spend a little time. We're going to do a short lecture and then talk about, well, go do the exam, the little quiz. And if you want to talk about things about the quiz tomorrow before we start it, we could talk about things about the quiz if you're interested.